Welcome to lecture number 12 for ECE476 Advanced Embedded Systems. Today we're going to look at the graphics display, finally getting to it. So this is the board that we're using in 476. It is the GeeekPi Pi Pico Development Board Plus version. It's got the I/O pins, push buttons, stuff like that. Big thing is it's got this graphics display. Today we're going to look at how to actually use that. So for example, here's a program that so here we're going to show off how to write your own library and introduce a library that drives the Pico's graphics. So this is a little routine that shows off some of the features that we'll be looking at, some subroutines that draw different things on the screen. I can put text on the screen. I can do a six-sided die that's kind of washed out, a playing card, circles, lines, boxes, numbers, all stuff we can do. So before we start, a little bit of how the Pi Pico works. In Thani, when I do File, Open, I can open files from the computer or the Raspberry Pi. On the Raspberry Pi, stop the program, File, Open, Raspberry Pi, you're going to need a couple of routines. You need to save the lcd.py on the Raspberry Pi. I've also got two other routines, LCD 16 by 24, 24 by 32. These are various LCD routines. They've got prettier character graphics, but they take up more room. Main.py. If you want a program to run on boot up, save it as main.py on the Raspberry Pi. Just save it there, and then when you power up, that's what executes. Currently what I have on there is something that just clears the graphics display because we haven't been using it yet. And another library matrix. That'll be coming up in a couple lectures. So to use these routines, you've got to take the program lcd.py and copy it over to your Raspberry Pi. Once you do that, you'll have access to the LCD routines. So that's kind of where we're heading. How do you use the LCD graphics on the Raspberry Pi? So the graphics display that comes on your GeeekPi board is a 480 by 320 graphics display. What we're talking about today is the library, LCD. This isn't a standard Python library. It's specific to this board, something written specifically for this class, 476. It's free for anyone to use. Basically, the Pi Pico-W only came out in June 2022, so there's not a whole lot of software for it yet. The GeeekPi board, just an absolute lovely board, love it, but there isn't a whole lot of software for it either. So we had to write our own driver routines for the LCD. Again, to get these routines to work, you got to copy them to the LCD or to your Pico chip, and then you'll have access to them. Now, a little bit of background. The graphics display is driven by an ST77964 chip. It's hardwired to your Pico board on pins 2 through 7. What that means is if you want to use the graphics display, don't use 2 through 7 for other stuff. They're kind of tied up. Some pins you kind of can use. The SPI, clock, data in, data out can be used. There's also a chip select. The chip select is pin 5. Give your device a different chip select and you can reuse those pins. But generally, you don't want to use pins 2 through 7 if you're using the graphics display. In addition, the graphics display communicates using SPI protocol. So what happens is to talk to the display, I need to bring the chip select line low. Chip select is pin 5. That initiates conversation. I need to tell it, am I sending it a command or data? Like data would be I'm writing to the display, a command would be clear the display. I have to send it data, most significant bit first, and clock in the data. The data is valid on the rising edge. And there are dozens and dozens of commands on the ST77964. The ones we'll be using for driving the graphics, abbreviated list, is command 1. That's a software reset. 11, that's the wake up. 3A, set the color mode to 16 bits per pixel. 2.9 turns on the display. 2.1 turns off inversion. So a 1 is color, 0 is dark. 2A is set range column. 2B, set row range. And 2C, memory write. There's other commands as well, but that's the main ones we'll be using. And cut a note. When you write to the display, the main routines that are used in the LCD library is a set column range, set row range, and memory write. That speeds it up. Kind of the way it works, if I set row range, say to x0, y0, this will set x0 and x1. That sets the column. If I then set the row, I've defined a rectangle. When I do a memory write, that fills in this rectangle left to right. When I reach the right endpoint, it comes back and kind of goes left to right all the way down. This is a faster way to write to memory. I can write the data at 40 megahertz using this technique. What this means is that I can write horizontal lines really fast. I'll just define a rectangle that is like 200 by 1 and fill it in at 40 megahertz. I can define vertical lines very fast. I'll define a 1 by 200 rectangle and fill it in. Diagonal lines are really slow. Diagonal lines, I kind of have to go pixel by pixel. So what you're going to see is on the display, anytime I do horizontal vertical lines, it's pretty fast. Diagonals are kind of slow. So when you're setting up your graphics, try to avoid diagonal lines. And that shows up in the execution time. If I draw a horizontal line, it only takes 3 milliseconds. A diagonal line, 300 pixels long, is 179 milliseconds. What is that? 80 times, 60 times longer. If I want to draw a rectangle has got nice horizontal vertical lines. It takes 1.6 milliseconds. To draw a circle the same size is 200 milliseconds. So basically, try to avoid things that aren't horizontal vertical. In addition, when I'm putting text on the screen, what really happens is I'm using the memory write command to define a rectangle. That's the size of the text. All text is the same size. For example, the default text is 8 by 16 font. I'm going to set up an 8 by 16 rectangle and then set up a bunch of spaces in memory. 0 is off or dark. Some other number is the color that I'm writing. I'll then write to the memory, left to right, and fill it in. This uses a lookup table. The first row, 0, 0 would be all off, 0, 0, 1, 0. Hex 1 is 0, 0, 0, 1, 0, 0, 0, 0. This tells you which pixels to turn on. I've got a table that basically tells you which pixels to turn on. This set of numbers corresponds to the letter capital A. Now there's a couple different fonts in the LCD library. The main one is an 8 by 16 font that takes up 10K of RAM, and it's kind of blocky, but it's quick, doesn't take up a lot of memory. There's a 16 by 24 font, which is prettier, but takes up 31K. The font I really like is a 24 by 32 font, but that takes up half the memory of the processor, 62K. So maybe it's not such a good idea. But it is available just because I put it in there, didn't want to delete it. And these are available in different libraries. So if you go back under Thani to File, Open, Raspberry Pi, these are the different LCD libraries. This one is the normal one. If you open it, these are the different routines. There's a little help. If I type in help, lcd.help, it tells you the different commands. And here's the font. These are the different letters from the ASCII table. Then the various commands we'll talk about in a sec. If you go to the open. Where's File Open? File, open. There you are. This uses up 125K of memory. Takes a while to load. Same as LCD.Pi, but scroll down. It's got a couple different fonts. It's got the 24 by 32 font. Here's the, and that takes up a lot of memory. I'll store it in memory map. So just so you know. For color encoding with the ST77965, there's two ways of doing it. I can do 6-bit colors, red, green, blue, or a 565 format. This routine actually uses the 565 format. The reason being is it only uses up 2 bytes to store color. The 6-bit color uses up 3 bytes. That means I can write to the display 50% faster using only 2 bytes. So everything in this routine uses the 565 format. The way that it works is if I have a 16-bit number, the high 5 bits define red from 0 to 100%. The middle 6 is green. The right 5 are blue. Now the routines inside the LCD library, we'll talk about these in more detail a little bit later. I've got to import the LCD. That gives you access to all these different routines. There's help. If you type in help, you can see what's happening on the LCD. Initialize the LCD has to be called once, otherwise the LCD doesn't work. I can return a 16-bit number for a specified color. 255, 255, 255 is full brightness, red, green, blue. That gives you white. Vary the ratios. I can get up to 65,000 different colors. Clears the display of a certain color. I can write to a pixel, draw a line, draw a box, draw a solid box, do a bar chart, display playing dice, display a playing card, shuffle a deck of cards, do a bar chart, plot X versus Y, and put a title on it. So that's what's inside the LCD library. I can also draw to the screen in a couple different fonts. LCD text, right to the screen. Text 2 is the double scaling, bigger fonts. Text 3 is a prettier font, 16 by 24. LCD text 4 is the prettiest font, 24 by 32, but used up gobs of memory. And likewise, I can put numbers on the screen using the various fonts. So again, the whole goal today is to introduce this library and kind of show you what you can do with it. Again, the Pi Pico doesn't come with a library for the LCD display. There isn't a whole lot of documentation on how to drive it in Python. Here we've got some Python routines. So let's start out with initialize and color. If I say import LCD, define navy as no red, no green, 20 blue, 255 is full, off. Initialize, clear the display. That's what it looks like. In terms of Thani, go to LCD clear. I can change a color. LCD dot, oops. LCD.RGB of 0, 0, 0, 20. This will clear the display, initialize and clear it, so all this will go away and just see a navy screen. There. Clear display. If I want to try a different color, like let's do a pink, dark pink. 20 red, green, blue. Really bright red, bright blue, kind of washed out. So anyway, that's what clear does. Let's go back to, and on my camera's kind of sensitive to color, so I kind of do 5. That shows up as a nice dark blue. That's LCD clear. Color. I can specify different colors. Again, this goes red, green, blue. 255 is full brightness, 0 is off. So if I have all red, that's red, all green, all blue. Everybody in there is white. Gray is equal weighting, dimmer color. Black is all off. First function, box. I can draw a box on the screen. If I specify the color of the box, again, here's the box, I'm going to specify the upper left corner. This guy right here is 50/50. On the x-axis, this goes from 0 to 479. Y, it goes from 0 to 319. This says where the upper left corner is at 50/50, the lower right corner is at 100, 100. And the color of the box I want to be pink. So I define the colors, and just to kind of illustrate how long it takes to execute, I'm going to record the time before I call box, record the time afterwards, and display on the LCD. This is the execution time. So a box took 4.6 milliseconds to draw a 50 by 50 box in pink. Let's draw a solid box. What the solid box does is a little bit different than box. What box does is it just draws a line, 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 line. A solid box actually defines a rectangle that's in here, fills it in with all the same color. So if I just define the color of the box, again, the upper left corner is 50/50, the way I called it here. Bottom right corner is 100/100. Color is pink. Everything in here is the same color. It's a solid pink box. If I want to draw a line, like let's draw an octagon. With a line, I specify the starting point, the end point, and the color. So this is the actual line command. I'm going to go from the first point to the second point in that color. Here I defined an array that defines an octagon for 0 through 8. Go at the center, which is 200, 150, right here. That's 200, 150. Go around a circle with 8 points, and then connect the points. That gives you an octagon. And this actually takes a while to draw because the lines aren't horizontal or vertical. That actually took 113 milliseconds to draw that shape. So lines that aren't horizontal vertical are definitely much slower. There's a circle command. For example, right here, I am going to draw a circle. There it is. The origin is right here at 150, 150. The radius is 100, and the color is pink. So I define the colors, initialize the display, clear it with a navy background, draw a circle. That took 814 milliseconds to draw. Again, kind of slow. What it has to do is go pixel by pixel around the circle. To send out text. Again, one of the great things about the graphics display is it's much easier to get data out. We can send data out on the Thani window. Again, like over here, I'm able to get data out. The problem with that, well, that's actually really nice while you're programming it. The problem is if I want a standalone device, like have this be a device that, I don't know, the user can type in numbers on the touchpad, on the touch screen. I don't actually have a keypad or a screen for the user to see. I can't put the information right on the graphics display. Now, when I do that, I've got a couple different fonts. If I use the default font, LCD text or LCD number, these are 8 wide by 16 fonts. Pick whatever color you want. When I write the color, I actually fill in the whole rectangle. Color 1 is the color of the text. Color 0 is the background. So for all these, I made the background color navy, so it looks like it's just written right on top of the background. With text, you just have a message, tell it what the message is, tell it where you want the upper left corner to be. Again, this point right here is 0, 0. This is X is 479. This on Y is 319. Specify where you want to put the text, and then it sits there, it starts right here, and then writes left to right. Let's see. For number, I can also specify how I want it formatted. This uses a fixed decimal format. N is number of digits, and M is the number of decimal points. So there's M, and this is N. For example, if I write this code, I'm going to define the colors, define 3 different texts. Write the first text at 0.55, that's right here, 55. Pink text with a navy background gives me the first row. The second one are lowercase characters at 5x, 25y in yellow. The third set of text is in cyan, the navy background. That's text. For numbers, let's just take the square roots from 1 through square to 9. Display that as 10 digits, 7 decimal points. So that's 7 decimal points. The total number of digits is 10. I'm going to place that X at 5. The Y, there's X. Here's the Y point. So each one comes down, adding 20 to it, against an 8 by 16 font. 8 by 16. So if it just come down 16, it'll be right next to it. I came down 20, so there's 4 blank spaces between each one. And set the color. So this is your red, green, blue. As I get pure red initially towards green, kind of show off some colors. Text 2 is the same as text, but it's scaled by 2. So again, it's an 8 by 16 font, scaled by 2. So the net result is a 16 by 32 font that's kind of blocky, but it writes pretty quick. Doesn't take up a lot of memory. Same code as before, just what that looks like. That's text 2 and number 2. Same code, just change that to a 2. For text 3, this is a 16 by 24 font, a lot prettier, kind of font that I like. Trick with this one is I need to import the LCD 16 by 24 library as LCD. It says, call this library LCD, it's now available. So everything's the same except I can now use text 3, and it uses up an extra 30K of memory because I have to store that font. Text 4 is even prettier, a bigger font, but that takes up an extra 60K of memory. To use it, I need to import LCD 24 by 32 as LCD. Then I have access to text 4. If you try to write text 4 using a different font, it just gives you an error message, doesn't display anything, and continues on the merry way. So that's the text font. There's Pixel. What Pixel does, that's used in the circle command, it just highlights a single pixel. Pixel 2 by 2 highlights a 2 by 2 array of pixels, kind of like a thick line. If I want to use it, like draw a circle, what I can do is for 314 points around the circle, basically 2 pi r, go to x0, y0, x coordinate is plus r cosine theta, y is r sine theta. So I'm going to go from this point, go all the way around, and when I'm done, what it looks like is a circle. Now this is actually kind of slow, 214 milliseconds, because I got to go pixel by pixel. There's LCD light. This is kind of set up if I want to mimic the I/O pins on the Pico chip. I want to say which pins are on, which ones are off. I'm just going to draw a rectangle, a small square, either that's hollow or solid. The solid represents the LED is on, hollow's LED is off. Just thought it'd be useful. And binary out, if I send a number like 76, it will display it in binary. Solid is 1, hollow is 0. There's also a bar chart. That's the same thing. If I do 0, they're all off. If I do 1, this one turns on. This is 2, 3, up to 16. Which LED is turned on? That's another thought might be useful. Dice. Kind of anticipating that later on we're going to be rolling dice and doing programs with dice. If you want to play craps or D&D or something like that, it might be kind of nice to display some dice. Well, that is the LCD function dice. This is the number 1 through 6. Here's where I want to put the die. That's the corner XY. The first color is the color of the pips. In this case, it's red. The second color is the color of the die. In this case, it's white. So if I do the roll, pick a random number for D1, pick a random number for D2, and display it, here I rolled a 2 and a 6, or 2 and a 4, like that. Playing cards. Just kind of guessing that someday we'll be writing some routines that shuffle decks and play things like poker or blackjack. You can display a playing card. When you display a card, I've got the value. The value can be 1 through 13. 1 is an ace, 2 is a 2, 3, 4, 5. 11 is jack, 12 is queen, 13 is king. The suit is 1 through 4. 1 is clubs, diamonds, hearts, spades. And XY is where you want to put the card. To shuffle a deck, there's the function LCD sort. I pass it an array of numbers, and it will sort the data and return, this is the sort order, which card was the smallest, which number is the next smallest, and so on. That's used in LCD shuffle. This generates a 52 by 1 array of random numbers, sorts it, and tells you what the sort order is. So the net result is numbers 0 through 51 in random order. With that, I can basically tell you which card is which. So like 0 would be the ace of spades or ace of clubs. 1 is the 2 of clubs, 2 is the 3 of clubs, and so on. For example, if I want to deal out 5 cards at random, I would say initialize, my hand is 5 cards, the value of each card, the suit of each card, shuffle the deck. I will then take the first top 5 cards in the deck and copy them into my hand. The value of that card is the hand mod 13 plus 1. Again, 1 through 13 is the result. The suit is the hand integer divided by 13 plus 1. Display the value in the suit at this location. And you see the first card that I drew was the 5 of spades, 2 of clubs, king of diamonds, 3 of spades, 7 of hearts. So we print out what my hand is. Here's the hand. First card is card number 48, which is the 10 of spades. Card number 36, which is the jack of hearts. Card number 7, which is the 8 of clubs. And card number 32, which is the 7 of hearts. He keeps on dealing out a different hand, and that shows up like this. So presumably later on we can start playing poker. Next, let's look at the bar function. This is similar to the MATLAB command bar. It creates a bar chart with your data. The color of the edges is the second one. The fill is the third one. So what the bar chart does is, given a string of data, the x-axis is just the value, the first entry, second entry, third entry, and the height is the data within x. For example, if I want to display something like an ice storm spell, I can input the numbers. This is the number, different ways you can roll each number. Define the colors, and then do a bar chart with the data. The edge is white, the fill is light blue, and add a title. Doing something similar, but with a fireball spell. That's a bar chart. Next, let's look at a plot command. And this is very similar to the MATLAB command plot. It'll plot x versus y. It automatically scales the axis, so the max and min are in the y direction, and x max, x min in the x direction. X is just a scalar or an n by 1 vector. Y can have a couple of data sets. If you just have a single data set, you get a single plot. If you have multiple data sets, you'll get multiple plots. For example, if I want to plot a sine wave versus its harmonics, x, well, start out with the 100 data points in each array. X is just time, steps of point 1. Y is sine of t, y1, sine, the first 2 harmonics of a square wave, first 3 harmonics, first 4 harmonics. To illustrate that, I'm going to have x go between 0 and 10. Y is the first harmonic of a square wave, first to third, fifth, and seventh. As I run that, you get your graph. So those are some of the routines you can have that are available in the LCD routine. It's still a work in progress, but what it does for you, it gives you access to the LCD display, so you can draw lines, rectangles, playing cards, dice, polygons, text in 65,000 different colors. The standard font is 8x16, which isn't real pretty, but it's pretty fast and doesn't take a lot of space. Larger fonts are available, but they use up a lot more memory. So now that we have the LCD routine, we're going to start using that for the rest of the semester as a way to get data out. Again, the advantage being is if you put the PIC or the Pico in standalone mode, you're not connected to a keyboard, you're not connected to a screen. If you want to get data out, the graphics display is a way to do that. And that's lecture number 12 for ECE476.